Alright, let's take a look at different types of data. First thing we're going to look at is whether something is a parameter or a statistic. A parameter is a numerical measurement describing some characteristic of a population. A statistic is a measurement, a numerical measurement, so same as previous, describing some characteristic of a sample. So they're both numerical measurements. One of them describes a characteristic of a population. One of them describes a characteristic of a sample. There's a very easy way to remember the difference. Parameter, population. Statistic, sample. Alright, so some examples of a parameter would be things like there are exactly 100 senators in the 109th Congress of the United States, and 55% of them are Republican. That 55% of them are Republican, that is a parameter. Now, I don't know exactly if those percentages were correct to today's Congress, but that's an example of a parameter. A statistic would be something like this. In 1936, Literary Digest polled 2.3 million adults in the United States, and 57% of them said that they would vote for Alf London in the presidency. So that 57% is a statistic because it is based on a sample, not a population. The Literary Digest got 2.3 million people as their sample of citizens, I guess, from the United States. So parameter is a percentage or a decimal or something about a ratio about a population, whereas statistic is a percentage or a ratio about a sample. All right. Let's look at a couple of problems. See if we can figure out, is this a statistic or a parameter? These problems are in the back of the section, so let's see if we can figure them out. In a AAA Foundation for Traffic Safety survey, 21% of the respondents said that they recently texted or emailed while driving. So, do you think that would be a statistic or a parameter? A statistic. That 21% of the respondents, that would probably be a small sample, right? It's not going to be. You think that this survey included everyone that drives in the world? No, probably not. Okay, so that's a sample, so that would be a statistic. Number 6, there are 50 state capitals in the United States. Would that be a statistic or a parameter? 50 state capitals. Does that include every state capital in the United States? Yes. Okay, so that is a parameter. A study was conducted of all 2,223 passengers aboard the Titanic when it sank. That's about the whole population of people that were on Titanic, including Leonardo DiCaprio. All right? We couldn't be so lucky, could we? Just kidding. Number 8. Among the flights included in the sample of flights in dataset 15 of Appendix B, 21% arrived late. Well, you know what? This one just kind of tipped us off there. There's a key word in there. But yeah, if it's a sample, then that gives us a statistic. Yeah, I like that. All right, IQ scores. The mean IQ score for subjects taking the Western Adult Intelligence Scale IQ test is 100. All right, so is that from a sample? Let's see what happens if I click this right here. Or from a population. What is that talking about? And let's see if I can get back to that page. Oh yeah, I could use the back button. Imagine that. That's black magic. I can't use that. It's tricks. It's tricks. No, I'm just playing. Anyway, I haven't used this interface very often, but it is important that you understand and get used to it. Let's see. Are we in 1.3? Yes, we are. Just down a little bit. All right. We're looking at the IQ scores. So this mean IQ score, would this be from a sample of people, or would this be from everyone that takes the IQ test? It's from everyone. So that's why this right here, this mean of 100 is a parameter, because it comes from the entire population of people taking the IQ score, or IQ test, excuse me. Number 10, the average atomic weight of all the elements in the periodic table is 134.355 unified atomic mass units. So all the elements, it's going to be a population, so parameter. Brain volume. I guarantee you my brain volume is huge. All right, the average volume of the brains included in dataset 6. Now that I read that, that's pretty nasty, because they actually got volumes of brains and put them in a dataset. All right, is 1,126.0 cubic centimeters. Is that talking about a sample of those, or every one of them in these dataset? It's a little confusing, isn't it? The average mean volume of brains included in dataset 6 of Appendix B is 1,126. Me personally, I see that as a population, because they took all those brains and that's the whole dataset. But if you think about it, why would we say that's a statistic?
It's dataset 6.
Yeah, dataset 6 in Appendix B. I don't think that's everybody's brain. Maybe just one small data set. So sometimes you got to read over these a couple times, because you might think it's a parameter, but it's really a statistic. You just got to kind of think, does this include everything? You know, everyone that has a brain? No, of course not. It just includes a small sample of brains. I feel like I should be on a zombie show or something, talking about brains. Alright, one more. HDTV penetration. In a random sample of households, it is found that 47% of the sampled households had high definition TVs. Does anybody in here not have a high definition TV? I don't think you're all participating. Is there anybody here that does have a high definition TV? Yeah, okay. This book was probably written about a year or two ago, and high definition TVs are the thing, right? Everybody wants a high def, especially when it comes to sports. Man, it looks so much better. So this 47% of, what's that? Sampled households. So is this a parameter or a statistic? A statistic. All right. Let's see. Let's look at, this will be the last topic we cover for now. Let's look at continuous data Or no, let's see what's next. Let's look at quantitative and qualitative data. Now, I usually just call it quantitative and qualitative. You can see here your textbook says quantitative data or numerical data consists of numbers representing counts or measurements. Quantitative or numerical data consists of numbers representing counts or measurements. When I hear quantitative, I think about quantity, a number. So quantitative data consists of numbers representing counts or measurements. Categorical or qualitative, and your book says or, attribute data consists of names or labels that are not numbers representing counts or measures. I usually just call it qualitative. So, qualitative data consists of names or labels that are not numbers representing counts or measurements. So it's either quantitative or it's not, it's qualitative. So one or the other. So if I have ages of people in a survey, is that going to be quantitative or categorical? If I had ages of people, that's going to be quantitative because those are numbers, those are ages. Okay? If I had a set of data that told me everyone's hair color in here, then that would be the categorical or qualitative data. All right? Let's say that I had a set of data and it told me whether you were Democrat, Republican, or independent. That would be categorical or qualitative data. But if I had another set of data that was everyone's weight in here, that would be quantitative data. All right, so you see the difference? Now let's take a look at discrete data and continuous data. All right, textbook says that discrete data result when data values are quantitative and the number of values is finite or countable. So quantitative and the number of values is finite or countable. And, you know, the key words here that I would remember about discrete data are that it is quantitative and finite or countable. Really, countable is the key word for discrete data. So if we have, say, maybe we own a farm and our chickens laid 15 eggs last night. You know, those eggs are countable. We get good solid whole numbers. We don't have 15.2 eggs one day and 17.9 eggs the next. Those eggs are a countable value, so those are discrete data. Right, continuous data. Your book says they result from infinitely many possible quantitative values where the collection of values is not countable. So I know that usually whenever you refer to your weight, you use a whole number. You know, you'll say, you know, I weigh 512 pounds or I weigh 126 pounds. But think about if you had a scale that was really, really precise. Your weight from day to day would change. Maybe I weigh 150.279 pounds one day, and then the next day I weigh 152.34926 pounds the next day. There are an infinite number of possibilities of your weight if you carried out the decimal place far enough, if you had that precise of a scale. Things that result from infinitely many possible values, those are continuous. You know, the height of a tree may be 97.2578 inches one day, and then it may go up by a 10,000th the next day. That's not something that we would consider discrete or countable data. That's something that is continuous data. Okay? So let's take a look at some of the problems in the book or in this text. See if we can figure out whether the values are discrete or continuous. All right, Honda Civic crash test. In dataset 13 of Appendix B, the measured chest deceleration of a Honda Civic in a crash test is 39 grams, or 39 G, sorry, where G is a force of gravity. Okay? So, what do you think? Discrete or continuous? Is that really a value that is countable? Know that it's a whole number, so you might be thinking, well, it sounds countable to me. Do you think that the chest deceleration of every Honda Civic is going to be exactly a whole number? I mean, it would really depend on how they rounded, but something like that would be something kind of like your weight or your height. There are no holes or gaps, meaning it is continuous. Let's look at a few more. The Honda Civic has 4 cylinders. Can a car have 4.2 cylinders? Well, if you don't know much about cars, then you probably wouldn't know, which is, you know, that's a fair question. But for those of you that do know a lot about cars that have cylinders, can a car have 4.2 cylinders? 4.6 cylinders? No. 4 cylinder, 6 cylinder, 8 cylinder gas guzzlers. The higher the cylinders go up usually. So that means that 14 would be what? A countable value. It would be discrete. All right, word count. From dataset 17 in Appendix B, we can see that a male spoke 13,825 words in one day. Can you speak 13,825.6 words in a day? No, the number of words that you speak, if they are indeed words, is going to be countable. So that means that 15 is discrete. 16. First president, George Washington, was 188 centimeters tall. That would be continuous because it involves a height, and heights can vary, right? And you can, you know, your height does change over time. Actually, once you get to a certain age where you're not getting any taller, then you start getting shorter again as gravity starts working on you. Maybe not much, not noticeably much. You're not going to come in tomorrow an inch shorter. But heights can be decimals. You know, like in the previous problem, words, you can't really measure words in a decimal. House of Representatives. Currently, the House of Representatives has 435 members. Discrete. It's countable. You're not going to have at any time, any day, at any country, well, this does say House of Representatives, so it is talking about our country, but you're not going to have 435.2 members, right? You're just going to have a whole number. So that means that the House of Representatives, number 17, would be countable or discrete. Number 18, crash test results. Dataset 13 in Appendix B includes crash test results from 21 different cars. That's right, discrete. You can't have results from 21.2 cars. You know, you're going to have a whole number there, always. Earthquake, number 19, data set 16 in Appendix B. It says we see that an earthquake had a measurement of 0.70 on the Richter scale. Continuous, that's right. And the last one, number 20, arm circumference. From data set 1 in Appendix B, we see that a female had an arm circumference of 27.5 centimeters. Continuous, that's right. You can get very many values, decimal values for that, so it's continuous. Okay. So we have data sets. Let's say we have a bunch of data sets. How can we classify those data sets? Some data is more useful than others. Well, it really depends on what type of study that you're looking at. So let's now look at the different levels of measurement. The levels of measurement depend on the type of data that you have. Okay? There are several levels of measurement. The first one that we're going to discuss would be considered the, I guess, the simplest. The one that is characterized by data that consist of names, labels, or categories only. So, names, labels, or categories only. That's called the nominal level of measurement. This is the simplest level of measurement. Alright, the nominal level of measurement is characterized by data that consist of names, labels, or categories only. Also, the data cannot be arranged in an ordering scheme. Such as your book points out, yes, no, undecided. If a survey has that, let's say that I had a bunch of those results, yes, no, and undecided. There's not an ordering scheme like high to low or low to high that I could sort those in. What if I did another survey of this class and I said, oh, okay, I want you to tell me, are you Democrat, Republican, or Independent? How would I order those? Yeah, I could sort them, but ordering them from highest to lowest, no. There's no ordering scheme that would make sense that way. So that would be a nominal level of measurement. All right. Now look at this third example, Social Security numbers. Now you might think, oh wait now, we all have a Social Security number, and we can sort numbers from lowest to highest. But would that really have any meaning? Why would you want Social Security numbers listed from lowest to highest? Just because my number comes after your number, that doesn't mean that I make more money or that I'm older or whatever. So if it doesn't have a meaning to be ordered, it could be ordered, but there's no meaning behind it, it's still a nominal level of measurement. Okay. The next level of measurement we're going to look at is called the ordinal level of measurement. All right, the ordinal level of measurement is used when we have data that can be arranged in some order, but the differences obtained by subtraction between the data values either cannot be determined or are meaningless. All right, so it's kind of like a step up from nominal, if you want to think about it like that. So data can be arranged in some order, but differences either cannot be determined or are meaningless. All right, some of the examples given in this textbook are course grades. So if I took everyone's grade in here and I assigned the proper letter to your grade, I could order them like highest to lowest, because everybody in here wants an A, and everybody in here knows that if you get a B, an A is higher than a B. However, if let's say that you get an A in the class and I get a C in the class, and that's all we know, if I say A minus C, that doesn't give me a B. I can't get something meaningful from subtracting if your grades are just A, B, C, D, or F. So that puts that type of data set at the ordinal level of measurement. Ranks. U.S. News and Report and World Report ranks colleges. As of this writing, Harvard was ranked first and Princeton was ranked second. Of those rankings, 1 and 2 determine an ordering, but the difference of those ranks is meaningless. You know, another example of a lot of sports fans in the world. You know, think about any kind of college sport. Usually they have a ranking, you know, the top 25. Well, if number 1 Florida State is playing number 6 Clemson, 1 minus 6 doesn't mean anything. Now, Florida State is higher ranked, so that does have that meaning, but 1 minus 6 is not going to tell me anything about that data set. All right. The next level of measurement we're going to look at is the interval level of measurement. All right, so with the interval level of measurement, the data can be arranged in order differences in data values can be found and are meaningful. So differences can be found and are meaningful. And this data does not have a natural zero starting point. The data, this is very important, does not have a natural zero starting point. All right, so temperature does not have a natural zero starting point. You can sort temperatures this week, and you can subtract or find differences. You can say Monday's temperature minus Tuesday's temperature, and you can find something that's meaningful. It was 5 degrees colder on Monday, or it was 5 degrees warmer on Tuesday, or whatever. But zero, that's not where temperature starts. So that temperature does not have a natural zero starting point.
So this is an example of an interval.
These are examples of the interval level of measurement. If you had a set of data and it was temperatures, it would be at the interval level of measurement. If you had a set of data and it's at years, that's also the interval level of measurement. You can sort those, or you can arrange those in order, like high to low, low to high. You can find differences, and the differences have meaning. If you were born in 1990, I was born in 1977. 1990 minus 1977. So that tells you that I'm probably around 13 years older than you. Most of you are probably born in what, 2000, right? Something like that. Just kidding, just kidding, just kidding. All right, the next level of measurement is the ratio level of measurement. All right, the ratio level of measurement, data can be arranged in order. Differences can be found. There is a natural zero starting point. All right, for data at this level, differences and ratios are both meaningful. Differences and ratios are both meaningful. So, for example, car lengths. You know, if you went out and you had a set of data, you'd measured a bunch of cars. That don't sound very exciting, but let's say you had that set of data. You could arrange those from least to greatest, greatest to least. A car that measures 0 in any units is not a car, right? It has a natural zero starting point. You know, you say, well, how would you get a 0? Well, maybe I said, okay, I want this set of data. I want the length of everybody's car in here. But then some people don't have cars. Maybe they have trucks. Maybe they don't have a vehicle. So then, you know, if I wanted everybody's data, they would have a 0 down for their data. Okay. Ratios, differences are meaningful. So the length of one car minus the length of another car. That could be found and could be meaningful. Maybe your car length over my car length, or your car length over the average car length. That ratio could probably be used somewhere. All right, so that is meaningful. Class times. The times of 50-minute and 100-minute for a statistics class. 0 would represent no class. 100 minutes is twice as long as 50 minutes. Okay. There's a little hint under this level of measurement. It says this level of measurement is called the ratio level because the 0 starting point makes ratios meaningful. Here is an easy test to determine whether values are at the ratio level or not. Consider two quantities where one number is twice the other and ask whether twice can be used to correctly describe the quantities. Because a person with a height of 6 feet is twice as tall as a person of height 3 feet, the heights are at the ratio level of measurement. In contrast, 50 degrees Fahrenheit is not twice as hot as 25 degrees Fahrenheit. So Fahrenheit temperatures are not at the ratio level. Okay. Your book then gives you a table with a description and some examples. In case you get confused, you could look back at that table. So let's take a look at these problems where we need to determine the level of measurement. See, colors of M&Ms, red, orange, yellow, brown, blue, and green, listed in data set 20 in Appendix B. Alright, so could we say about those M&Ms? We need to look at the different levels and see the differences. So like nominal, you have labels or categories. The data cannot be arranged in an ordering scheme. That's the most basic. Well, that kind of sounds like that data set. We could group them. We could sort all of our M&Ms. I like to do that with Skittles sometimes, which I don't try not to eat a lot of Skittles, but I like to group them in different colors. But, you know, orange minus brown doesn't tell me that green's the best. So it's just a real simple data set. So the level of measurement would be nominal. Okay. Number 22, depths of earthquakes listed in dataset 16 of Appendix B. We can subtract those depths. They can be ordered from highest to lowest. A depth of 50 feet is twice as much as a depth of 25 feet. So that is a ratio level of measurement. Is there a natural zero starting point? Yes, a depth of 0 would be no depth at all. All right, number 23, years in which U.S. presidents were inaugurated. Interval. Years, remember, no zero starting point. So it doesn't have a natural zero starting point, so that's why it's interval. 24, the movie Avatar was given a rating of 4 stars on a scale of 5 stars. All right, ordinal. "25 volumes of brains listed in dataset 6 of Appendix B." Kind of creepy, but ratio. You have a natural zero starting point. You can subtract, you know, the volume of one brain from another brain, and that has some type of relevance. Number 26, car models. Chevrolet, Aveo, Honda Civic, Buick, used for crash testing as listed in dataset 13 of Appendix B. All right, that's at a real simple level. There's no way to arrange those highest to lowest. You may have an opinion, but with that set of data, you should, you know, opinions don't matter with a set of data. At least not that set of data. Blood lead levels of low, medium, and high used to describe subjects in dataset 5 of Appendix B. That's number 27. Ordinal. Body temperatures listed in dataset 3 of Appendix B. Again, it's a temperature, so it doesn't have a natural zero starting point. So that's why it's interval. You may have thought ratio, but temperatures don't have a natural zero starting point. Your body can be colder than 0 degrees.